Hi. Thanks for the organizers to organize this nice workshop, and thanks for hanging around for this talk. Typically, we're in North America, so planets don't migrate. Let's get a work on how this happens in our modern models of protoplanetary disks, and this is actually going to be more or less an overview of planet migration. To round out the workshop was a little bit awkward, but sure. So, um, where we start from is a model of the structure of a protoplanetary disk. I've seen this a few times before. The driving thing behind what's happening in the field these days is understanding the non-ideal MHD effects and the fact that the disk has a very hard time being turbulent through it and viscously driven through the whole thing. It probably gets driven by a magnetothermal wind, which mainly drives an accretion flow across the top layer, leaving the midplane in the few AU region where we want to do a lot of our plant formation relatively unmolested by viscous effects like the turbulence. So you can run numerical models of that, and here's an example of that from collaborators and myself. Of this, you see here the velocity field forming this wind, this relatively laminar midplane region, and these quite smooth magnetic fields where even in the upper regions, the ambipolar diffusion is quenching out the flow and keeping it nice and smooth. So, what happens when you drop a planet into a disk? It's a bit of a review for anybody who maybe hasn't run into this before. Yeah, set this up. I've dropped a planet in here to a disk. It's migrating in. It's causing a response to the gas surface density, and that is, in return, is causing a torque on the planet. And we can think of that as being made up of contributions from these two spiral wakes, the inner one pulling forwards and the other one pulling back, and it's cancellation between those two, which will set the torque on the planet. There's also material in the co-rotation region, co-orbital region here, which makes these horseshoe turns encountering the planet, and the asymmetry between the angular momentum exchange on these two will, again, lead to a contribution to the torque. So these things naturally depend on the parameters of the planet and the disk. So what we can do is look at the behavior you get as a function of two of the most, there's many parameters, but two of the ones that are most interesting here are the planet mass as the planets grow and the disk turbulent viscosity, where on here at the high viscosity end of parameter space, we have viscous protoplanetary disks, and here in the low viscosity end of parameter space, we have wind-driven disks, and particularly the near midplane regions of those protoplanetary disks. Then each colored block here is a previously identified to various degrees regime of reasonably well defined behavior for planets migrating in disks. And then each of these gray streets is where there's some sort of critical parameter change that leads to a change in this behavior. So there's many citations for each of these. So this is the introduction section of that paper right there, which is a good place to go look these up if any of these are unfamiliar to you. So now that we know, compared to a lot of the previous work that's been done in planet formation, that we're probably not in a terribly viscous disk, we're in something wind-driven, and we can gray out this side of the diagram and focus on what's happening over here, where there's actually a lot of complicated and nonlinear behavior that comes up because we're in this low viscosity flow. So what I'm going to do now, in the remaining time, is try and work through examples of all these things and the differences back and forth here. So let's start at the bottom with a dynamical co-rotation torque in the low viscosity regime and a standard saturated, viscously unsaturated type 1 migration in the high viscosity regime. So I'm going to show you a little numerical experiment here where I do 2 runs in the same disk and the same planet, and then they run for a bit, and then I make a modification to each of those disks that's different for those two. Here, this disk becomes viscous, and there's accretion driven through it by that viscosity. And here, the disk is driven by a laminar magnetic braking torque that drives the flow in. So we'll start up here. We got our planets migrating in a viscous disk. These views here are the vorticity of the disk. You can see the co-orbital region there forming up, and down here, as that flash just happened, what happened was I turned on these either viscous effect or the magnetic braking torque. Here in this viscous disk, you see that the co-rotation torque has been unsaturated, and we're maintaining the background gradient of vorticity across there. So that leads to the asymmetry between the angular momentum exchange on those two horseshoe turns, and that planet just has a nice, steady, constant torque and just drives in. Something very strange is happening over here, however. You'll see that this planet, at the rate of that the disk is being driven in by this magnetic braking torque, the planet alone can't keep up with the disk flow from its Lindblad torques, so it gets kind of stuck behind, and the vorticity in the libration island actually reverses and runs away. So as this comes around here, you'll see that this saved up vorticity actually gets depleted and reversed to the other sign as the planet fails to keep up with the flow. And that leads to this very large positive co-rotation torque turning the planet around and driving out through the disk instead of in. So there's a big difference across this division here, also depending on what's happening in the rest of the disk. So let's move on. Going up a little bit in planet mass, we can get above the feedback mass, which is the parameter that comes up in the Goodman and Rafikov work for the planet starting to modify the disk surface density by its spiral wake. So in a viscous disk, the planet migrates in more or less in a type 1 manner and quite rapidly. The individual time series in these two animations are the same, so each frame is the same physical time. In this inviscid disk, however, that planet's moving a lot slower, and the structures it's driving are going unstable and causing a lot of Rossby wave instability, kicking off vortices. And so we're getting a quite different behavior there. So I want to dig into this a little bit more. Actually, we'll start with a little bit of viscosity, where we can get a smooth effect. And this lets us discuss the feedback slowing of migration, where these spiral shocks here are changing the vorticity of the disk, piling up mass, and that changes the balance between these two Lindblad torques. So a pretty old prediction coming up as the inertial limit concept from Ward and Hurigan, and then refined by Rafikov 2002. If I run that simulation here, you'll see that, again, this is the one I used earlier. That planet is able to get to a nice kind of steady, but much slowed from the type 1 rate migration due to the near cancellation of those migration torques. That can be arranged to happen with a little bit of viscosity to keep these nice and smooth. If you regard this because there's a bit of gap of type 2, then there's a bit of a question here about whether you want to call this maybe part of type 2 migration or not. And then there's an interesting thing of the data from here, which you can find in said paper, doesn't quite agree with things like the Kanagawa concept for type 2 migration. But I guess the last thing I should say there is that numerically this converges very well because I've got that viscosity to smooth out small scales of the flow. Now, the correct inertial limit prediction that you get from 1D models would be that the planet should actually kind of properly stop in an inviscid disk. So here's the inviscid version of that. And this is a resolution study. Here is slightly more than anybody's run before in terms of resolution on that problem. Here's a little bit more than 2 times, and here's a little bit more than 5 times the resolution anybody's run before. That's up to 93 cells per scale height. And you see that at the lowest resolution I have, the planet actually does slow down from the type 1 rate and eventually nearly stop, but then vortices that arise in the edge of the gap and those pressure bumps start to free the planet up again, and it drives in faster. That behavior kind of, it actually then gets into kind of a type 3 jump. That behavior continues at higher resolution, and at the highest resolution here, we get this behavior where showing the vorticity, these vortices that both come up at the outer edge of the gap and on the edge of the libration region lead to this very jumpy migration and rearrangement of the disk, which instead of stopping the planet leads to this slow interaction with vortices driving it in a wobbly manner. So this brings up the issue of whether this is converged, which I don't think you can actually say it's converged. But also at the same time, I'm up to 93 cells per scale height in a two-dimensional model of the disk. So for this problem, this is probably the highest resolution two-dimensional simulation that anybody should ever run. We've hit a limit here on how we can consider this behavior. But it's clear that the inertial limit that you predict from the one-dimensional models, as you go to 2 dimensions, at least that seems to fall apart, and the planets don't stop. Now, quickly I'll show you a scan across viscosity from high viscosity to low to show this change in behaviors. So the highest viscosity, I can get something that agrees quite well with the type 1 migration rate. As I go down to a little bit lower in viscosity, we actually get, this is a heavy enough planet that it drops into type 3 migration immediately. As I go to lower viscosity, it's able to modify the shocks are able to modify the disk quickly enough to end up in that smooth feedback I showed you. And then at lower viscosity, the vortices which form, you can see here, are freeing it up compared to the smooth feedback rate. And it actually ends up jumping into its, the density bump it's pushed in front of it inwards in a type 3 behavior. Although these types of behavior in 2D are quite resolution dependent. So now just to finish up here around the last corner here, a little quick bit of type 2 with vortices. If you go to very high mass planets, what we see then is once we have gaps that are depleted by several orders of magnitude from the background, that the planets move initially until they sit in their deep gap and then are freed up when there is matter released by the gap edge instabilities that can then interact with the planet. So this is part of the story with what's happening in type 2 at low viscosity. Now, what we've been recently doing, and I promised Phil I'd show a bit of when I came, is to go into 3 dimensions on some of these things. This is clearly needed. So we've got a grant out of price, the European Tier 0 allocation system, and we've been running Fargo at quite high resolution with quite big grids on this. And here's some of the results. So this is a comparison between, again, a 2-dimensional vertically integrated model of an adiabatic section of the disk with a planet just above the feedback mass. And this is the libration region. And you can see the classical Korokensky Baumforth type behavior with these vortices at the edge of the libration island. And then you'll see as the planet moves in, we get a situation like one expects for classical dynamical co-rotation torques, where the vortensity of the libration island looks like the color from where the planet started. However, in 3 dimensions, something totally different is happening. We're getting an enhancement of vortensity, not a preservation. So it's clear that something very important is happening here with the difference between 2 and 3 dimensions, beyond also just how these vortices interact and decay or don't, because 3 and 2-dimensional vortices behave very differently. There's a little bit of a clue of what that is I can show you here. If I keep the planet fixed, these 2 movies, again, this just well mixes by background vortensity. Here, it's not the movement of the planet that's leading it, it's inherently the 3-dimensionality of the flow that's leading to this vortensity or vertically integrated vortensity-like quantity enhancement. And the net effect of this is once you have the planets moving, that introduces an asymmetry to the shape of this libration island. This has a negative co-rotation torque contribution, whereas in this situation, the usual dynamical co-rotation torques give you a positive co-rotation torque contribution. Now, the last thing I want to get onto is a little bit related to what Daniel just showed you, where he was using long chains of planets with a lot of mass in them that would eventually push in and then sometimes undergo dynamical instability to result in chains of planets which are not in the end in mean motion resonances, as we find that most of the things in the Kepler sampler aren't. So here's a contrast between considering migration in a viscous disk, as he just did, and a disk which is inviscid. So the experiment, this is actually just a This isn't nearly as ambitious an attempt at prediction. This is a attempt at an apples-to-apples numerical comparison between these two scenarios for a disk. What I've rigged here is a disk which in both cases has a turbulent and decreasing in density inner edge, so the planets pile up against, and then an outer region, which is here, viscous all the way through, and hence a model for turbulence, and here, inviscid in the outer region. You'll see these red orbit circles that are piling in as the planets come in both cases. In the viscous case, planets compress into a nice chain of mean motion resonances, whereas in the inviscid case, you see that the vortices, these C-shaped bright things that pop up as the planets are able to feed back into the disk, add extra perturbations to the system and allow these planets to undergo close encounters and reorganize. I can show you that a little bit more clearly if I show you the semi-major axes of the planets versus time. And here, in the viscous case, they compress into this nice smooth resonant chain. In the inviscid case, the extra perturbations allow the planets to have close encounters, and it sequentially compresses into this much tighter configuration, sometimes with planets out of resonance. Then that's only part of the problem, though. We do have to worry about what happens when the disk goes away. So if we do this, we add a phase in the simulation where we dissipate the disk on some time scale and then transfer into a pure n-body evolution. We see that in the viscous case, the chain of planets in the mean motion resonances stays stable for a long time. Here, I've only integrated them out to 100 million years. They're stable in the viscous case, mostly stable in the viscous case, whereas the inviscid case, again, here only with 5 planets as opposed to a very long chain, they tend to go unstable, and then also sometimes you seem to get lucky and find a configuration which doesn't appear to be in such mean motion resonances, but does seem to have long-lived stability. So it looks like there's an important difference between what one might predict for the formation of systems of planets in an inviscid disk versus a viscous disk once you have these super-Earth mass planets. So that's actually, I managed to get through that in good time. So yeah, we now understand that planets form in these inviscid wind-driven disks. Once we understand that, we know we have to be working with planet-disk interaction theory over on this side of the diagram, and we get very different predictions than what one might have expected for the traditional viscous disk things. And that actually poses a very significant computational challenge because 2 dimensions often isn't enough. We need inherently often to do things like the last thing I showed you, probably very long integration times in multi-dimensions. And there's then also the issues of actually dealing with the wind and such issues, particularly up here. So, I'm on there. Thank you.
Thank you. Perfect time, even early. Questions? Yes.
What happens to eccentricities and inclinations in these low viscosity cases? I mean, of course, it's an old prediction that if the gap is very clear, there should be some excitation, or there might be some excitation of eccentricity.
So you're asking particularly up here?
Yeah, I guess.
Well, okay, so with this, we haven't gotten into doing so much work on yet. So that's an interesting question. There is a little bit of eccentricity that comes out due to the vortices that I've seen here, but for the most part, this hasn't been something we've actually gone into too much yet. So this is one of the many things that does get interesting again once we're at low viscosity.
Of course, it's potentially constrainable, especially the inclinations.
Yeah, yeah.
Systems that we observe.
Yeah.
Yes.
I'm not sure how useful this question is, but just
doesn't hurt. We got time.
Is there any reason we should think that a turbulent alpha viscosity will behave similar to a viscosity for this type of problem? Because you're talking about a boundary layer in some way between these regions, right? I mean, is there a reason
Okay,
we
so
should
I think
they're
you're
similar?
asking if I could paraphrase that in the way I like to say it, is that is alpha a good model for alpha viscosity, a good model for the actual diffusive effect of turbulence on this problem?
Yeah, because you're particularly caring about this one region, really. I mean,
Yeah,
I
as
can see
opposed
it
to
as in many cases, but for this particular case, it's
yeah,
not
because
enough.
there's very localized
Exactly.
regions of the flow
Yeah.
that we really care about that have particular contrast going
Right.
in them.
You're seeing this big change
Yeah.
basically because of a change in this localized region.
Yeah.
So,
Well, I think the answer is no, and that hasn't been taken seriously enough by the community. Yeah, that's actually something that probably needs some work. Something like lots of high-resolution DNS, and then trying to compare that back to Reynolds averaging the flow back again. Yeah, because a lot of what's kicking off these state vortices is Rossby wave instability, and I don't think alpha is a good predictor for what Rossby wave instability tends to build, and its diffusive effect if there really is that much of building those big vortices. So it's probably not a great model anyway. So in that sense, I'm putting viscosity in here because that's what we do, but turbulence and viscosity may be different.
Yes.
On that, it
Yeah.
reminded me of an old bee in my bonnet. There's the fact that it's layered accretion might make you suspicious of representing MRI as a viscosity, if that's what John
Yep.
Lloyd's asking about, but also time dependence. So this ordinary viscosity of gases, because the collision frequency is so high compared to frequencies in the flows, is essentially constant in frequency.
Yep.
But MRI, or pretty much any turbulence, definitely has a characteristic timescale which is comparable to omega.
Yep.
So if you have disturbances which are at high frequency compared to that, such as vortices are one thing, but even worse, spiral waves.
Yep.
It's not at all clear that they see that the viscosity that damps spiral waves is the same for a given turbulence as the viscosity which causes axisymmetric gap edges, for example, to spread. I wish someone would do a simulation where you force a spiral wave in an MRI turbulent disk and measure the damping length.
Yeah, I think actually Richard Nelson,
Okay,
if
maybe
anybody has
sorry.
done the closest to that. The difficulty with that is now we're probably not in MRI turbulent disks, wind-driven disks.
Yeah, okay, but it's
Yeah.
still,
It's
there are other disks, maybe
yeah.
not protoplanetary
Well,
disks, which are
it's very
MRI
relevant to
turbulent.
the work Mordecai is doing on black hole accretion disk.
Okay, well, I'll go read his paper.
Yeah. So no, this is a direction clearly I think things have to go. Finally, at the end, we're getting into this discussion.
Yes, Vlad.
Yeah. So this map there, I mean,
Yeah.
I would call it migration town, right?
Okay.
A village.
Migration town.
Yeah.
Well, it's one version,
Oh.
right? There probably should be things sticking out this way with other parameters,
Right.
right?
I was wondering that if the color coding of the blocks, do they mean anything like the growth rates,
No.
the damping times? No.
No,
You can do
I
that,
went
right?
to a color palette generator website because I have very bad color vision, and so I got hex codes and filled them in. My wife hates this color scheme, by the way.
And by the way, what viscosity is here?
Okay, so we tried to basically write a review of the references for each of these things in this paper. So it's actually it's a good thing to look at. This especially down here is pretty much predicted by Samyan's work on the viscous unsaturation of co-rotation torques. So that, of course, sorry. Yeah, that's around alpha 10 to the minus 3-ish. But it depends. It does depend. So there's some very purposeful kind of wobbliness to these because it does depend on the planet mass because it depends on the width of the co-rotation region. But it is, turns out, viscous unsaturation is exactly the thing that gives you the, when you saturate the co-rotation torque is precisely where dynamical co-rotation torques come in for the precise same reasons that you're stopping unsaturating them. So it's exactly that change. That's actually one of the best defined of these.
And that's the same as the viscous smoothing up there?
Yeah, this one and this one aren't really well defined. So this one's actually in here drawn in at an angle because if you look then at say this paper for the same viscosity for two different planet masses, the low mass planet definitely gets a feedback modified. Vortex and feedback modified migration, whereas the higher mass planet has the smooth migration. So somebody should go out and work out exactly some kind of a theory for what the parameter changing on that is. And this one is also just kind of filled in that way because at high viscosity, you don't get a vortex when you go in type 2, and at low viscosity, you do.
Yeah, I guess the question was really what is the viscosity below which you have.
So this is in the alpha 10 to the minus 4-ish region. Although that's only for the higher mass planet that we managed to do a convergence study of on there.
Okay. Is there any other question? Okay. If not, I think Phil wants. Would you like to say something? Yeah. Well, first of all, let's thank Colin and Daniel. And maybe you want to say something.
Yeah, so just briefly, I guess first of all, I'd like to thank everyone for coming. Speaking for myself, I had high expectations for the meeting, knowing who was coming, and my expectations have been exceeded. So thank you very much. I'd like to encourage you. There'll be more meetings here at the CCA in the future. So, and also, if you're just passing through New York, we have a lot of visitors here, and we're delighted to welcome visitors. So if you have new results, come and present them at group meetings and just stop by. So please do consider that. And then finally, hope everyone agrees it was well organized by the CCA staff. So thanks to Abigail, to the AV people and the other people who've been helping, and maybe we can just give them a round of applause.